This is standard 7.2, recognizing and evaluating series. This particular standard is on geometric series. If you want to look at arithmetic series, there is another standard 7.2 video about that on my website. This video will also include infinite geometric series and sigma notation. So our first example says find the sum of the first 7 terms. And if we look at our sequence here, we can see that it is geometric. And the way that we can tell is that we can identify a common ratio. So to find our common ratio, you pick any term in your sequence and divide by the term in front of it. And in this case, we get negative 1/2. And if we did that with a different pair of terms, like negative 5/2 divided by 5, we also get negative 1/2. Or if we take 5/4 divided by negative 5/2, you also get negative 1/2. Stop and check this with the calculator. Make sure you're getting these same values. You probably want to put your fractions in parentheses on your calculator unless you have one of the newer models. Alright, so since we have a ratio here that's common, it's always negative 1/2. We know that it's geometric. And our job is to find the sum of the first 7 terms. So the formula for the sum of a geometric sequence is the following. And all we're doing is substituting, and our quantity is 7, so that goes in for n. T1 is our first term, negative 10. 1 minus, and r is negative 1/2. Now be careful, you have a minus from your formula and a negative on the r. And n is 7. So 1 minus negative 1/2. Now here's something that a lot of you are probably going to do. You're going to see 2 minuses and change that to a plus. And that's a no-no because our power 7 comes before the subtraction. So we have to take negative 1/2 to the 7th power first before we decide what we're doing with those negative signs there. Now, one of the tougher parts of this type of problem is actually evaluating on your calculator. So I suggest you do it piece by piece. I might do negative 1/2 to the 7th power first. When you're raising a negative value to a power, you want to put it in parentheses. So negative 1/2 to the 7th power is negative 1/128, or 0.0078125. Now, I'd rather use the fraction, and I definitely don't want to round because then my sum is not going to be accurate. Alright, so I did the exponent first, and now we can do what's in parentheses, and now these two negatives, yes, become a positive. So if I add them together, again, I can do this as a fraction or a decimal, but you know your fraction key on your calculator, so use it for precision. 129/128, and then 1 minus negative 1/2 is 3/2. And then just finish off on your calculator. And your sum for the first 7 terms ends up being negative 6.71875, or negative 215/32, which in my opinion is definitely a nicer looking answer. Alright, second example, we want to again find a sum, and let's check for a common ratio r first. So 2.88 divided by 2.4 is 1.2, and 2.4 divided by 2 is also 1.2. So since our ratios are common, they're both 1.2, we verify that it's geometric. So since we're finding the sum, we're going to use our sum formula again. S sub n equals T1 times 1 minus r to the n over 1 minus r. And just looking ahead a little bit, we can see that we have T1, we have r, but we don't know n. We don't know what term number 4.97664 is. So at this point, we can use our formula for geometric sequences and plug in to find n. So T1 is 2, r is 1.2, n is unknown, and Tn is the term that goes with the unknown n. So that's 4.9 lesson check. Since my exponent is a variable, I'm going to use logs. And to solve this exponential equation, we convert it to a log equation. So our base is 1.2. Our argument is 2.48832. Your newer calculators have a log button that does this for you. Older calculator, like mine, we're going to have to do the log of the second number divided by log of the first number. And that works out to 5. Now if you get a decimal for n, you know you've done something wrong, because n is a counter for our terms, and so those are going to be positive integers. So n is equal to 6 here. Alright, now we have enough information to plug into our formula. So we're finding the sum of the first 6 terms. Our first term is 2, r is 1.2, n is 6, over 1 minus 1.2. If you're going to put the whole thing in your calculator, make sure you put the denominator and numerator in their own sets of parentheses, otherwise your calculator is not going to have the correct order of operations. So let's see how this works. We're going to do 2 parentheses 1 minus 1.2 to the 6th power. So closing both sets of parentheses in the numerator, divided by, and in parentheses 1 minus 1.2. Close the parentheses on the denominator, and our sum is 19.85984, which will it give it to us as a fraction? It will. So either of these are acceptable answers. 19.85984, or the fraction equivalent. Alright, example 3, evaluate this sum. Now notice here that our sum is infinite. It goes on forever. And so let's take a look at the first few terms and then determine the type of series it is and see if we can actually find a sum. So let's start by plugging in our lower limit here, 4 for n. So we have 4 times 2/3 to the 4 minus 1. So that's 4 times 2/3 to the 3rd power, which is 4 times 8 over 27, which is 32 over 27. That's our first term. Now our second term, we're going to plug in the next integer up from 4, which is 5. So 4 times 2/3 to the 5 minus 1. So that's 4 times 2/3 to the 4th, which is 4 times 2 to the 4th, and 3 to the 4th, which ends up being 64 over 81. And let's just do one more. 4 times 2/3 to the 6 minus 1. So 4 times 2/3 to the 5th power. So that's 4 times 2 to the 5th, which is 32, and 3 to the 5th, which is 243, which works out to be 128 over 243. And this is an infinite sum, so it is going on forever. So we have a formula for the sum of an infinite geometric series, which is S sub infinity equals T1 over 1 minus R. Now the conditions on using this formula is that our series is in fact geometric and that the absolute value of R is less than 1, otherwise the sum doesn't exist. So let's confirm that it's geometric. Notice in our numerators we're multiplying by 2, and on denominators we're multiplying by 3, and so it appears that R is 2/3. And if you go back and look at the original expression, it's exponential, and that's enough to tell us that it's geometric. And your growth rate, B, 2/3, is like your R value, and that is indeed less than 1. And since our growth rate is less than 1 and it is geometric, we can use our formula for the sum of an infinite geometric series. T1 is the first term in our series, which is 32 over 27. last example here to condense into sigma notation. So here we have a sum. Let's decide if it's arithmetic or geometric. If we look at our first, I'm going to put it over 1. The numerators are not changing, so the numerator you're multiplying by 1 each time, but the denominator you're multiplying by 2. So it appears that r is equal to 1 over 2, or 1/2. Now you can test that out by taking any term, like 3/4, and dividing by the term in front of it, and you can verify that r is indeed 1/2 and that it's common. So if I take, for example, 3/2 and divide by 3, I also get 1/2. So it's geometric. And when we set this up in sigma notation, we need our starting value, we need the last value of n we're going to plug in, and we need a formula. So our starting value makes sense to start with n equals 1, and our formula would be for a generic term. So our formula for term is Tn equals T1 times r to the n minus 1. Keeping n generic, so we can plug in any value of n we wish. T1 is 3, r is 1/2 to the n minus 1. By the way, those are my children yelling in the background. I apologize if you can hear them. Alright, so this is our expression for our geometric series, and you can check by just plugging in a value for n. Like, let's plug in n equals 3, and we should get our third term 3/4. So we plug in 3, we get 3 times 1/2 to the 3 minus 1, which is 3 times 1/2 squared, which is 3 times 1/4, which is 3/4, and yes, that matches. So our first value is n. Now we have to figure out what goes in green in here. What's the last value that we plug in so that we get 3 over 256? And we can find that by using our formula again for a term in a geometric series. But now we're trying to find n, which is our counter, our quantifier. How many terms do we have here in the sequence that we're adding up? So T1 is 3, r is 1/2, n is unknown, and let's choose our last term, 3 over 256, because that's what we want the n for. So if we do that, and we divide both sides by 3, we get 1 over 256 equals 1/2 to the n minus 1. You might recognize 256 as a power of 2. It's 2 to the 8th. So you can write this as 1/2 to the 8th equals 1/2 to the n minus 1. And when you do that, your common bases cancel out. 8 equals n minus 1, or n equals 9. So 9 is the last number that you could plug in there to get that last term. Now, if you could also use logs if you wanted to find n. So let me just squeeze that in this little space right here. So instead, you could have changed this to log base 1/2 of 1 over 256 equals n minus 1, and done change your base formula 1 over 256 or log of 1/2, and that works out to be 8, and gotten n equals 9 that way as well. And so in sigma notation, our expression is the following. That's what we're trying to find here. Now, of course, you could find the sum by using the formula for a sum, but in this case, we're not being asked to do that. This is standard 7.2, and this specific